Hello there, and welcome to Earth's History, where we ask the biggest questions, where we look at our planet not as a random accident, but as something that might have been intentionally crafted, where we examine the staggering number of coincidences that had to align perfectly for life, for us to exist. Tonight, we're contemplating something profound and unsettling. What if Earth wasn't an accident? What if the precise conditions that allow life, the exact positioning of our planet, the specific properties of our moon, the mathematical constants appearing in nature, and ancient structures, what if all of this was designed? What if we're living on a planet that was deliberately engineered, prepared, optimized for life by an intelligence we can barely comprehend? If you've ever wondered why Earth seems almost too perfect for life, if you've noticed how many things had to go exactly right for us to exist, if you've looked at the mathematical elegance in nature and ancient monuments and felt there's a pattern too precise to be random, you're touching on one of the most profound mysteries of existence. Are we the product of blind chance, of random physical processes operating over billions of years? Or is there evidence, subtle but persistent, that Earth, and perhaps the universe itself, were designed with intention, with purpose, with us in mind? Wherever you are right now, I hope you're comfortable, settled, ready to drift through questions that blur the boundaries between science and philosophy, between the physical and the metaphysical, between what we can measure and what we can only wonder about. Maybe you're lying in bed as darkness deepens. Maybe you're in that quiet, contemplative space where big questions feel natural rather than threatening. Maybe you're ready to consider possibilities that challenge everything you thought you knew about reality. If this journey into the nature of existence brings you wonder, if it helps you see Earth with new eyes, if it opens your mind to mysteries that science hasn't yet resolved, I'd be grateful if you'd like the video, subscribe to the channel, or share it with someone else who isn't afraid to ask whether the universe might be more than it seems. So settle in. Let your breathing slow, like the patient rotation of Earth on its axis. Let your thoughts expand like the universe itself, reaching toward questions that have no easy answers. And let's begin. The Goldilocks planet. Too perfect to be random. Let's start with the most obvious evidence: Earth's position in the solar system. We orbit the Sun at an average distance of about 150 million kilometers, a distance astronomers call 1 astronomical unit, or AU. This distance places us in what's called the habitable zone, or Goldilocks zone. Not too close to the Sun, not too far, but just right for liquid water to exist on the surface. Too close to the Sun, and water boils away. Venus, at 0.72 AU, experiences surface temperatures around 470 degrees, 880 degrees show, hot enough to melt lead. Its water was lost billions of years ago, boiled away into space, leaving a hellish world with crushing atmospheric pressure and sulfuric acid clouds. Too far from the Sun, and water freezes solid. Mars, at 152 AU, is cold, with average temperatures around 80 degrees. Any water on its surface is frozen into ice or locked in the soil. Mars probably had liquid water billions of years ago when it was warmer, but it lost its atmosphere and became the frozen desert we see today. Earth, at 1.0 AU, sits right in the sweet spot. Our average surface temperature is about 15 degrees 6, 59 degrees 6, perfect for liquid water. Perfect for life. Water covers 71% of Earth's surface, cycles between solid, liquid, and gas, drives weather systems, creates the conditions for life. But here's what makes this suspicious. The habitable zone is narrow. Current models suggest it extends from about 0.95 AU to 1.37 AU, a range of only 0.42 AU in a solar system that extends dozens of AU. Earth sits almost perfectly in the center of this narrow band. If we were 5% closer or 15% farther from the Sun, conditions would be dramatically different, possibly incompatible with complex life. Is this luck? Random chance? Or does it suggest intentional placement? The skeptical response is straightforward. There are hundreds of billions of stars in our galaxy, most with planets. With so many planetary systems, some planets will inevitably fall in habitable zones purely by chance. We exist on one of those planets because we couldn't exist elsewhere. This is the anthropic principle, which states that we observe conditions compatible with our existence, because if conditions were incompatible, we wouldn't be here to observe anything. This is logically sound, but somehow unsatisfying. Yes, with enough random trials, unlikely outcomes become probable. But when you examine the specific details of Earth's situation, not just the orbital distance, but dozens of other factors that all had to be right, the just luck explanation starts feeling insufficient. Let's look at those other factors. The magnetic shield, Earth's invisible protector. Earth has a magnetic field generated by convection in its liquid iron outer core. This magnetic field extends thousands of kilometers into space, creating the magnetosphere, an invisible shield that protects us from solar wind and cosmic radiation. The sun constantly emits charged particles, the solar wind, streaming outward at hundreds of kilometers per second. Without Earth's magnetic field, this solar wind would strip away our atmosphere over millions of years, the same fate that befell Mars. Mars once had a magnetic field, but its small core cooled and solidified. The magnetic field disappeared, and solar wind gradually stripped away much of the Martian atmosphere, leaving the thin, cold atmosphere that exists today. Earth's magnetic field deflects most solar wind around the planet, preventing atmospheric loss. The field also protects life from harmful radiation, both solar radiation and cosmic rays from outside the solar system. High-energy particles that would damage DNA and make the surface uninhabitable are mostly deflected or absorbed by the magnetosphere before reaching the ground. Why does Earth have a strong magnetic field while Mars doesn't? Size matters. Earth is larger than Mars, about twice the diameter, which means more internal heat, which means the core remains molten, which generates the magnetic field through the dynamo effect. If Earth were significantly smaller, our core might have cooled and solidified like Mars, eliminating the magnetic field and making the surface inhospitable to life. But size alone isn't enough. Earth also has the right composition. Enough iron to form a substantial core. Enough radioactive elements to generate internal heat through decay. The right balance of materials to maintain a molten outer core while having a solid inner core. The dynamics are complex and depend on numerous factors that all have to be right. Venus, which is similar in size to Earth, doesn't have a significant magnetic field. Why not? We're not entirely sure, possibly because Venus rotates very slowly. One Venusian day is 243 Earth days, which might not generate enough dynamo action to sustain a magnetic field. Or possibly because Venus's core composition is different, or because its internal dynamics are different for reasons we don't fully understand. The point is, having a protective magnetic field requires multiple conditions to be right. Planet size, core composition, rotation rate, internal heat generation, possibly other factors. Earth got all these factors right. Coincidence or design? The Moon, our improbable companion. Let's talk about the Moon, because Earth's moon is weird. It's much larger relative to its planet than any other moon in the inner solar system. The Moon's diameter is about 27% of Earth's diameter, and its mass is about 1.2% of Earth's mass. For comparison, Mars's moons Phobos and Deimos are tiny. Phobos is only about 22 kilometers across, essentially captured asteroids. Venus and Mercury have no moons at all. The Moon formed about 4.5 billion years ago, most likely from debris created when a Mars-sized object, called Theia, collided with the early Earth in a glancing blow. This impact threw enormous amounts of material into orbit, which coalesced into the Moon. This is called the giant impact hypothesis, and it's well supported by evidence, including the Moon's composition, which closely matches Earth's mantle, and computer simulations that show such an impact can produce a Moon-like object. But here's the thing. This impact was incredibly specific. Too direct, and Theia would have simply merged with Earth, increasing Earth's mass but not creating a large moon. Too glancing, and Theia would have bounced off or passed by without sufficient material being ejected. The angle, velocity, and size of the impactor all had to be within a narrow range to produce the moon we see today. What are the odds of such a perfect collision? Hard to calculate precisely, but probably low. Giant impacts were common during the late stages of planetary formation, but most wouldn't produce large moons. Earth got lucky, or did it? Let's look at what the moon does for Earth, because its influence is profound. Tidal forces and life. The moon raises tides on Earth through its gravitational pull. These tides create the intertidal zone, the region of coastline that's alternately submerged and exposed. This zone is ecologically rich and important. Some researchers have proposed that tidal pools might have been crucial for the origin of life, providing environments where organic molecules could be concentrated, where wet-dry cycles could drive polymerization reactions, where the chemistry of life could develop. Whether or not tidal pools were essential for abiogenesis, the moon's tides have influenced the evolution of life. Tidal rhythms affect many organisms, from fish spawning cycles to migratory patterns to circadian-like rhythms in intertidal organisms. Life on Earth has adapted to tides, and tides have shaped ecosystems. Stabilizing Earth's tilt. More importantly, the moon stabilizes Earth's axial tilt. Earth's axis is tilted 23.5 degrees relative to the plane of its orbit around the Sun. This tilt causes seasons. When the northern hemisphere tilts toward the Sun, it experiences summer, while the southern hemisphere experiences winter, and vice versa. Without the moon, Earth's axial tilt would vary chaotically over millions of years. Computer simulations show that without a large moon, Earth's tilt could swing from nearly 0 degrees, no tilt, no seasons, to 85 degrees or more, extreme tilt, extreme seasons, with unpredictable changes driven by gravitational perturbations from Jupiter and other planets. Mars, which has only tiny moons, shows exactly this behavior. Mars's tilt has varied from about 15 degrees to 35 degrees over millions of years, possibly more in the distant past. These variations cause dramatic climate changes. When the tilt is high, Mars's poles receive more sunlight, polar ice sublimates, atmospheric pressure increases, and the climate is warmer and potentially wetter. When the tilt is low, ice accumulates at the poles, atmospheric pressure drops, and the climate is colder. Such dramatic climate swings would make it difficult for complex life to evolve. Life can adapt to gradual changes, but chaotic swings in climate over timescales of millions of years would be highly stressful. Species would need to be extremely adaptable, or would go extinct during unfavorable periods. Earth, with the moon's stabilizing influence, maintains a relatively constant axial tilt. Over millions of years, the tilt varies only slightly, between about 22.1 and 24.5 degrees in a predictable cycle. This stability has provided consistent seasons for billions of years, allowing life to adapt to regular, predictable climate patterns. Without the moon, complex life, particularly intelligent life, might never have evolved on Earth. The climate would be too chaotic, the environment too unpredictable. So the moon isn't just a pretty object in the night sky. It's an essential component of Earth's habitability, and its existence results from a highly improbable collision early in Earth's history. Designed, the moon-forming impact would be an odd thing to design. It was violent, catastrophic, and partially destroyed the early Earth. But the outcome was perfect. If you wanted to create a habitable planet, you'd want it to have a large moon for tidal and stabilization effects. Earth got one through what appears to be a cosmic accident. Or perhaps not an accident? The water mystery. Where did it come from? Earth has a lot of water. 1.386 billion cubic kilometers of it, covering 71% of the surface. But where did this water come from? This is one of the enduring mysteries of planetary science. Earth formed in the inner solar system, relatively close to the Sun, where temperatures were high enough that volatile materials like water should have been vaporized and blown away by solar radiation and the solar wind. The inner planets, Mercury, Venus, Earth, Mars, should be relatively dry, composed primarily of rock and metal with high melting points, yet Earth has abundant water. How? Several theories exist. Comets. Comets are icy bodies from the outer solar system containing large amounts of water ice. Perhaps comets bombarding Earth during the late heavy bombardment around 3.8–4.1 billion years ago delivered water. This was the leading theory for a long time, but there's a problem. The isotopic composition of water in most comets doesn't match Earth's water. Water molecules contain hydrogen, which comes in two stable isotopes: regular hydrogen, 1H, and deuterium, 2H, or D. The ratio of D to H in water, called the DH ratio, varies depending on where and how the water formed. Most comets measured have DH ratios significantly higher than Earth's oceans, suggesting they're not the primary source of Earth's water. Asteroids. Carbonaceous chondrite asteroids, which formed farther from the Sun than Earth, contain hydrated minerals and some water. These asteroids have DH ratios much closer to Earth's oceans. Perhaps asteroid impacts delivered most of Earth's water. This is currently the leading theory, but it requires a lot of asteroids hitting Earth, and the timing and mechanisms are still being worked out. Adsorbed on dust. Perhaps water was adsorbed, stuck to the surface of dust grains in the protoplanetary disk from which Earth formed. As these dust grains accreted to form Earth, they brought water with them. This water would have been incorporated into Earth's interior and later released through volcanic outgassing to form the oceans. Chemical reactions. Perhaps water was formed in Earth's interior through chemical reactions between hydrogen, which can be incorporated into minerals, and oxygen, abundant in rock. This internally produced water then reached the surface through volcanism. The truth is probably some combination of these mechanisms, but we don't have a definitive answer. The isotopic composition of Earth's water matches certain types of asteroids, suggesting they played a major role, but the details remain uncertain. Here's the design question. Why does Earth have so much water when nearby planets don't? Venus is similar in size and composition to Earth, but is essentially dry. Mars has water, but only frozen or in trace amounts in the thin atmosphere. Earth hit the jackpot. Water is essential for life as we know it. It's an excellent solvent. It remains liquid over a wide temperature range under Earth's atmospheric pressure. It has unusual properties, like expanding when frozen, that affect climate and geology, and it's the medium in which biochemistry operates. Without abundant liquid water, life on Earth would be impossible. The fact that Earth has abundant water, in the right place, at the right time, in the right form, seems like either extraordinary luck or evidence of design. If you were designing a planet for life, you'd make sure it had lots of water. The atmosphere. A delicate balance. Earth's atmosphere is 78% nitrogen, 21% oxygen, and 1% other gases, including argon, carbon dioxide, and water vapor. This composition is unusual and essential for life. Oxygen. The 21% oxygen concentration is particularly important. Oxygen is reactive, It's what allows combustion, rusting, and respiration. Complex life forms like animals require oxygen for metabolism, using it to extract energy from food through cellular respiration. But here's the interesting part. Earth's atmosphere didn't always contain oxygen. When Earth formed 4.5 billion years ago, the atmosphere had essentially no free oxygen. It was mostly nitrogen, carbon dioxide, methane, and other gases. Oxygen appeared gradually, produced by cyanobacteria, photosynthetic bacteria, starting around 2.4 billion years ago in what's called the Great Oxygenation Event. Before oxygen accumulated in the atmosphere, only anaerobic life that doesn't use oxygen, existed. The appearance of oxygen was actually catastrophic for most life at the time. Oxygen is toxic to anaerobic organisms, and the Great Oxygenation Event caused a mass extinction of anaerobic species. But oxygen also enabled the evolution of aerobic organisms, which could extract much more energy from food, eventually leading to complex multicellular life and animals. The current 21% oxygen concentration is optimal. Lower oxygen concentrations would make it difficult for large animals to get enough oxygen. Their metabolism would be limited. Higher oxygen concentrations would make fires more frequent and intense. At 25% oxygen, even wet vegetation would burn easily, and wildfires would be catastrophic. At 21%, we get enough oxygen for complex life, but not so much that the world is constantly on fire. Is this balance designed? The oxygen concentration is actually maintained by biology. Plants produce oxygen through photosynthesis. Animals and decomposers consume it through respiration and decay, and the balance between production and consumption keeps oxygen at roughly stable levels over millions of years. This is part of Earth's biogeochemical cycles, complex feedback systems that regulate atmospheric composition. Carbon dioxide. CO2 is crucial for life, despite its low concentration, currently about 0.04%, or 400 parts per million. Plants need CO2 for photosynthesis, and CO2 is a greenhouse gas that helps keep Earth warm enough for liquid water. Without greenhouse gases, Earth's average temperature would be about 18 degrees Celsius, 0 degrees Celsius, cold enough to freeze the oceans. CO2, along with water vapor and other greenhouse gases, raises the temperature to the current comfortable 15 degrees Celsius, 59 degrees Celsius average. But too much CO2 is disastrous, as Venus demonstrates. Venus's atmosphere is 96% CO2, creating a runaway greenhouse effect that makes the surface unbearably hot. Earth has mechanisms, primarily the carbon cycle, that regulate CO2 levels over geological time. Carbon dioxide dissolves in rainwater, forming carbonic acid that weathers rocks. The weathering products wash into the ocean, where they precipitate as carbonates and get buried in seafloor sediments. Eventually, plate tectonics subducts these sediments into the mantle, and volcanism releases CO2 back into the atmosphere. This carbon cycle acts as a thermostat, regulating CO2 levels and keeping climate relatively stable. Atmospheric pressure. Earth's atmospheric pressure at sea level is about 101 kilopascals, 1 atmosphere. This pressure is important because it determines the temperature range where water is liquid. At lower pressures, water boils at lower temperatures. On Mars, with atmospheric pressure less than 1% of Earth's, water can't exist as a liquid. It sublimates directly from ice to vapor. Earth's atmospheric pressure is just right to keep water liquid over a wide temperature range, allowing oceans, lakes, rivers, and rain. How did Earth end up with the right atmospheric pressure? It's determined by the total mass of atmosphere, which depends on many factors. Planetary size. Larger planets have stronger gravity and can retain more atmosphere. Composition of volatiles during formation. Volcanic outgassing over Earth's history. Loss mechanisms. Solar wind stripping. Atmospheric escape. And complex evolutionary processes. Again, multiple factors had to align to give Earth the right atmospheric composition and pressure. Each factor individually might be explainable by physics and chemistry, but the combination of all factors working together to create perfect conditions for life starts to feel less like coincidence and more like purpose. Plate tectonics. The recycling system. Earth is the only planet in the solar system with active plate tectonics, the process where Earth's lithosphere, the rigid outer layer, is broken into plates that move around, driven by convection in the underlying mantle. Plate tectonics shapes Earth's surface through multiple processes. Seafloor spreading. New oceanic crust forms at mid-ocean ridges, where plates diverge. Subduction. Old oceanic crust sinks back into the mantle at subduction zones where plates converge. Continental drift. Continents slowly move around, colliding to form mountains, splitting to form new oceans, volcanism, and earthquakes. Concentrated at plate boundaries, plate tectonics might be essential for life, for several reasons. Carbon cycle. As mentioned earlier, plate tectonics drives the long-term carbon cycle. Subduction carries carbon-bearing sediments into the mantle. Volcanism releases CO2 back to the atmosphere, and this cycle regulates atmospheric CO2 and climate over millions of years. Without plate tectonics, this carbon cycle wouldn't function, and climate might become unstable. Nutrient recycling. Plate tectonics brings nutrients from Earth's interior to the surface through volcanism, refreshing surface environments with materials that would otherwise be depleted. Mountain building through tectonic collisions also creates diverse habitats and drives erosion, which weathers rocks and releases nutrients. Magnetic field. Plate tectonics might help maintain Earth's magnetic field by facilitating heat loss from the core, maintaining the temperature difference that drives core convection. Without plate tectonics, Earth's core might cool faster or slower. This is debated, potentially affecting the magnetic field's longevity. Diversity of environments. The movement of continents creates diverse climates and environments, driving evolution. Continents splitting and joining affects ocean circulation, climate patterns, and biogeography, creating opportunities for speciation and adaptation. Why does Earth have plate tectonics, while Venus, similar in size and composition, doesn't? We're not entirely sure. Venus's surface appears to be a single rigid shell with no plate boundaries. Several theories exist. Venus might be too hot due to greenhouse effect, making the crust too plastic to form rigid plates. Venus lacks water, and water might be necessary to lubricate plate boundaries and enable subduction. Venus's rotation rate is too slow, affecting internal dynamics. Random differences in evolutionary history. The presence of plate tectonics on Earth depends on numerous factors: planet size, internal heat, composition, water content, possibly rotation rate, and possibly chance events in Earth's early history. Once again, multiple factors aligned to give Earth a feature that appears crucial for long-term habitability. If you were designing a planet for life, would you include plate tectonics? Probably, because it provides self-regulating climate control, nutrient recycling, and environmental diversity, all beneficial for life. The Jupiter Shield, our guardian. Giant. Let's zoom out to the solar system scale. Jupiter, the largest planet, orbits at about 5.2 AU from the Sun. Jupiter's mass is 318 times Earth's mass, 2.5 times the mass of all other planets combined. Jupiter is a gas giant, composed mostly of hydrogen and helium with no solid surface. Jupiter might act as a shield for Earth, protecting us from comets and asteroids that would otherwise bombard the inner solar system. Jupiter's immense gravity affects the orbits of small bodies throughout the solar system. When a comet enters the inner solar system from the distant Kuiper belt or Oort cloud, Jupiter's gravity can deflect it, eject it from the solar system entirely, or occasionally capture it, like comet Shoemaker-Levy 9, which Jupiter captured and then tore apart. with fragments eventually colliding with Jupiter in 1994. Without Jupiter, Earth would experience more frequent impacts from comets and asteroids. How much more? This is debated. Some models suggest Jupiter reduces impact rates on Earth by a factor of several hundred or thousand. Other models suggest the effect is smaller, or that Jupiter might actually increase some types of impacts by perturbing asteroid orbits. The truth is complex. Jupiter both deflects objects away from the inner solar system and occasionally sends objects inward by perturbing their orbits. The net effect depends on many factors and is still being researched. But on balance, Jupiter probably reduces the overall impact rate, particularly for long-period comets from the outer solar system. Frequent large impacts would be catastrophic for life. The asteroid impact 66 million years ago that killed the dinosaurs was about 10 kilometers in diameter and released energy equivalent to billions of nuclear weapons. An impact like that disrupts ecosystems globally, causes mass extinctions, and sets back evolution. If such impacts were common, every million years instead of every 100 million years, complex life might never develop beyond simple organisms that can recolonize after each catastrophe. Jupiter's presence might have been essential for giving life on Earth enough stability to evolve into complexity. Is this designed? Jupiter's formation resulted from the dynamics of the protoplanetary disk, with Jupiter forming where temperatures were cold enough for water ice to condense, increasing the solid material available for planet formation. This allowed Jupiter to rapidly accumulate a massive gaseous atmosphere. The specifics of Jupiter's location and size depend on the initial conditions and evolution of the solar system. In principle, explainable by physics, but in practice, each planetary system is unique, and ours happen to produce a large gas giant in the right location to serve as a shield. If you were designing a planetary system for life, you'd want a large gas giant in the outer system to reduce impact rates. Our solar system has that. Coincidence? Or part of a design? The fine-tuning of physical constants. Let's go even deeper. The fundamental constants of physics. The universe operates according to physical laws with specific constants: the gravitational constant, the speed of light, the strength of electromagnetic force, the strong and weak nuclear forces, the mass of fundamental particles like electrons and protons. These constants have specific values, and changing any of them would dramatically alter the universe. Here's the unsettling part. Many of these constants appear fine-tuned for life. Change them even slightly, and the universe becomes inhospitable. Stars can't form, atoms can't exist, chemistry becomes impossible, and life is precluded. The strength of gravity. Gravity is the weakest of the four fundamental forces, but governs the large-scale structure of the universe: planets, stars, galaxies. The gravitational constant determines how strongly masses attract each other. If gravity were stronger, stars would form more easily, but would burn faster and die quicker, possibly before life could evolve on planets orbiting them. If gravity were weaker, stars might not form at all, or might burn so slowly that they don't produce the heavy elements necessary for life. The strong nuclear force. This force binds protons and neutrons together in atomic nuclei. If it were slightly weaker, only hydrogen would be stable. No heavier elements, no chemistry, no life. If it were slightly stronger, protons would bind so readily that hydrogen would be rare, and the universe would skip straight to heavy elements during the Big Bang, resulting in a universe with no stable hydrogen, no water, and no long-lived stars. The electromagnetic force. This governs interactions between charged particles and is responsible for chemistry, light, and electricity. If it were stronger or weaker, atoms would be different sizes. Chemical bonds would form differently, and the chemistry necessary for life might not be possible. The ratio of electron mass to proton mass. The electron is about 1,836 times lighter than the proton. This ratio determines the size of atoms, the nature of chemical bonds, and the stability of molecules. Change it significantly, and chemistry as we know it becomes impossible. The cosmological constant, dark energy. This determines the rate of the universe's expansion. If it were much larger, the universe would expand so rapidly that galaxies, stars, and planets couldn't form. If it were much smaller or negative, the universe might collapse back on itself in a big crunch before life could evolve. These are just a few examples. Physicists have identified dozens of physical constants and initial conditions that appear fine-tuned. The ranges within which these constants must fall to allow a universe with stars, planets, chemistry, and life are often very narrow. Change some constants by as little as 1% or less, and the universe becomes sterile. This fine-tuning is called the fine-tuning problem, and it's one of the deepest mysteries in physics and cosmology. Why do the constants have the values they do? Why are they fine-tuned for life? Several explanations exist. Coincidence. Maybe it's just luck. The constants happen to have values compatible with life, and we're here to observe them because if they didn't, we wouldn't exist. This is true, but unsatisfying. It doesn't explain why the constants have these values. It just notes that they do. Multiverse. Perhaps there are countless universes, or regions of one vast universe, each with different values for the physical constants. Most universes are sterile, but a few, including ours, happen to have constants that allow life. We necessarily find ourselves in one of the life-permitting universes. This is the anthropic principle applied to the multiverse. The multiverse hypothesis is scientifically controversial because other universes are, by definition, unobservable, making the hypothesis difficult to test. Design. Perhaps the constants are fine-tuned because the universe was designed by an intelligence that chose values compatible with life. This is the design hypothesis, which resonates with religious and philosophical traditions, but is scientifically problematic because it doesn't explain the mechanism of design, doesn't identify the designer, and doesn't provide testable predictions. Undiscovered physical principles. Perhaps there's a deeper physical principle we haven't discovered that explains why the constants must have the values they do. Perhaps the constants aren't arbitrary, but are required by some fundamental theory. This would be scientifically satisfying, but remains speculative. We don't currently have such a theory. The fine-tuning of physical constants is compatible with the design hypothesis. If you wanted to create a universe capable of supporting life, you'd need to set the constants very precisely. Our universe has precisely set constants. Does this prove design? No, but it's consistent with design. The mathematical nature of reality. Let's talk about mathematics, because there's something strange about the relationship between mathematics and physical reality. Mathematics is a formal system of logic, dealing with numbers, shapes, patterns, relationships. It's abstract. Mathematical objects don't physically exist in the same way that rocks or stars do. You can't touch the number 3 or trip over a parabola. Yet mathematics describes the physical universe with unreasonable effectiveness. Physics is written in mathematics. The laws of motion, electromagnetism, quantum mechanics, relativity, all are mathematical equations. When we want to predict how something physical will behave, we write down equations, solve them, and the predictions match reality with extraordinary precision. Why does this work? Why is the universe mathematical? The physicist Eugene Wigner wrote a famous essay titled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences," exploring this mystery. He noted that mathematical concepts developed for abstract reasons often turn out to describe physical reality. For example, complex numbers, numbers involving the square root of 1, were initially considered abstract curiosities with no physical meaning. Then, quantum mechanics was developed, and complex numbers turned out to be essential for describing quantum states. How did abstract mathematics anticipate physical reality? Various explanations exist. Mathematics is discovered, not invented. Perhaps mathematical truths exist independently of humans, and we discover them by exploring logical relationships. Physical reality is mathematical, because reality itself is fundamentally mathematical in nature. This view, called mathematical Platonism, suggests there's a realm of mathematical forms or truths that exist beyond physical reality. Mathematics is a language. We invented. Perhaps mathematics is just a very useful language humans created to describe patterns. It works because we designed it specifically to match reality. This view suggests mathematics is a human invention, not a discovery, and its effectiveness is because we continuously refine our mathematics to fit observations. Selection bias. Perhaps only the mathematical concepts that describe reality get attention and use. We develop many mathematical ideas, but only those that map onto physical phenomena become important in science. We notice the hits and forget the misses, creating an illusion that mathematics is unreasonably effective. Reality is literally. Mathematics. Perhaps as some physicists and philosophers have proposed, physical reality is a mathematical structure. The universe doesn't just obey mathematical laws. It is mathematical at the deepest level. Matter, energy, space, time, all are mathematical relationships, and what we experience as physical reality is the subjective experience of existing within a mathematical structure. This last idea is radical and speculative, proposed by physicists like Max Tegmark in his mathematical universe hypothesis. If true, it would explain why mathematics describes reality so well, because reality is mathematics. From a design perspective, the mathematical nature of reality is intriguing. If the universe was designed, mathematics would be the design language. An intelligent designer capable of creating a universe would work with mathematical principles, setting up initial conditions and laws that unfold according to mathematical logic. The elegance and simplicity of physical laws, that complex phenomena emerge from a few fundamental principles, suggests intentional design to some thinkers. The universe could have been chaotic, arbitrary, with different rules in different places, requiring endless specific descriptions. Instead, the universe is governed by elegant mathematical laws that apply everywhere, suggesting an underlying unity and intention. Is this evidence of design? Not conclusively. The mathematical nature of reality could be explained by the alternatives mentioned above, but it's consistent with design and raises deep questions about why reality has the structure it does. Patterns in ancient structures, echoes of design. Let's return to Earth and look at human artifacts, because there's a curious pattern in ancient monumental architecture. Many structures incorporate sophisticated mathematical relationships, astronomical alignments, and proportions that seem too precise to be accidental. The Great Pyramid of Giza. This structure, built around 2560 BCE, encodes several mathematical relationships. The ratio of the pyramid's perimeter to its height is approximately 2p, chop p. The slope angle of 51 feet creates specific geometric relationships. The dimensions relate to Earth's size. Some researchers claim the pyramid is a scaled model of the Northern Hemisphere, though this is disputed. Internal passages align with specific stars that were important in Egyptian religion. Some of these relationships are certainly intentional. The Egyptians were sophisticated mathematicians and astronomers. Others might be coincidental, or the result of later researchers finding patterns in numbers. But the accumulation of mathematical relationships in the Great Pyramid is striking. Stonehenge, This monument, constructed in phases between 3000 and 2000 BCE, aligns with solar events, summer solstice sunrise, winter solstice sunset, and possibly lunar cycles. The precision suggests sophisticated astronomical knowledge and intentional design to function as an observatory or ceremonial site tied to celestial cycles. Angkor Wat. This Cambodian temple complex, built in the 12th century CE, encodes astronomical and mathematical relationships in its layout. The central tower represents Mount Meru, the cosmic mountain in Hindu and Buddhist cosmology. The temple's proportions and measurements relate to calendrical cycles and celestial movements. Mayan pyramids. The El Castillo Pyramid at Chichen Itza demonstrates sophisticated astronomical knowledge. On the spring and autumn equinoxes, the setting sun creates a shadow pattern on the pyramid steps that looks like a serpent descending the stairway, a visual effect requiring precise architectural planning and astronomical calculation. Teotihuacan. The layout of this ancient Mexican city incorporates a standard unit of measurement and precise alignments. The Pyramid of the Sun and other structures are positioned according to a master plan that relates to astronomical observations and mathematical ratios. What's the pattern? Ancient cultures worldwide incorporated sophisticated mathematical and astronomical knowledge into their most important structures. These weren't just buildings. They were cosmic diagrams, representations of celestial order, attempts to align human construction with universal principles. Why did they do this? Several possibilities. Religious, philosophical motivation. Ancient peoples believed in cosmic order, in harmony between heaven and earth, in the importance of aligning human activities with celestial cycles. Building monuments that reflected this cosmic order was an expression of religious devotion and philosophical understanding. Practical functions. Some alignments had practical purposes: tracking seasons for agricultural planning, creating calendars, timing religious ceremonies. The mathematics encoded in structures might have served as records or teaching tools. Inherited knowledge. Perhaps ancient builders were following plans or principles inherited from earlier, more sophisticated cultures. This is the ancient wisdom hypothesis, that there was an earlier tradition of sacred architecture that later cultures preserved and imitated without fully understanding its origins. Recognition of design. Perhaps ancient peoples recognized that the universe itself embodies mathematical principles, and they incorporated those principles into their structures as a way of connecting with the fundamental nature of reality. If the universe is designed with mathematical elegance, the most sacred human structures should reflect that design. This last interpretation is speculative but interesting. If ancient builders believed the universe was designed, they would naturally seek to incorporate elements of that design into their own creations. The prevalence of mathematical relationships and astronomical alignments in monuments worldwide might reflect a shared recognition across cultures that reality has an underlying order, a mathematical structure, a design that human works should honor and reflect. The anthropic principle. Are we seeing what must be? Let's address the skeptical counterargument directly. The anthropic principle. This principle states, in its simplest form, that we observe conditions compatible with our existence, because if conditions weren't compatible, we wouldn't be here to observe anything. Think of it like a lottery. Imagine 1 billion people buy lottery tickets, and one person wins. From that person's perspective, winning might seem miraculous. What were the odds? It must have been meant to be. But from an outside perspective, someone had to win. The winner's existence doesn't prove the lottery was rigged for them. It just proves that someone won, and that someone happens to be wondering why they won. Similarly, in a large enough universe, or multiverse, with enough planetary systems, some planets will inevitably have conditions compatible with life. We find ourselves on such a planet, not because our planet was specifically designed, but because we couldn't exist elsewhere. Our existence doesn't prove Earth was designed. It just proves that among billions of planets, some are habitable, and we're on one of them. This is a powerful argument that deflates much of the apparent evidence for design. Yes, Earth is perfectly suited for life, but only because life evolved here, adapting to Earth's conditions. Yes, the physical constants are fine-tuned, but perhaps there are countless universes with different constants, and we necessarily exist in one that allows life. The anthropic principle is logically sound. It explains the observations without requiring design. From a scientific perspective, it's preferable to invoke design because it doesn't require additional entities, a designer, and doesn't rely on untestable claims about motivation or purpose. But the anthropic principle also has limitations. It doesn't explain why anything exists. The anthropic principle explains why we observe life-compatible conditions, but it doesn't explain why the universe exists at all, why physical laws exist, or why the constants have the values they do. It accepts these as given and notes that we necessarily observe values compatible with our existence, but it doesn't provide deeper understanding. It requires many failed universes. The anthropic principle works best with a multiverse, countless universes or regions with different properties, most sterile, a few life-permitting. But the multiverse is speculative, unobservable, and unfalsifiable. We have no direct evidence for other universes, so invoking a multiverse to explain fine-tuning is, in some sense, replacing one mystery, fine-tuning, with another, the multiverse. It feels unsatisfying. This is subjective, but many people find the anthropic principle intellectually unsatisfying. It correctly notes that our observations are selection biased, but it doesn't answer the deeper question of why the universe has the structure it does. Saying, the constants are what they are, because if they weren't, we wouldn't be here, is true, but doesn't feel like an explanation. The specificity problem. The anthropic principle explains why we observe conditions broadly compatible with life, but it struggles with the specifics. For example, why does Earth have plate tectonics, which stabilizes climate? Why do we have a large moon, which stabilizes axial tilt? Many planets might be roughly habitable without these features, yet Earth has them. The anthropic principle would predict we'd find ourselves on a minimally habitable planet, because there are many more of those than optimally habitable planets. Instead, Earth seems optimized, which suggests either we're very lucky or there's something more going on. The anthropic principle is a valid skeptical response to design arguments, but it's not a complete explanation. It shifts the question from why is Earth habitable to why does the universe, or multiverse, exist with properties that allow habitable planets? The latter question remains open. Simulation. Hypothesis. Are we living in a designed reality? There's a modern twist on the design hypothesis that's gained attention in recent years. The simulation hypothesis. This idea, popularized by philosopher Nick Bostrom, suggests that we might be living in a computer simulation created by an advanced civilization. The argument goes like this. Technological progression. If civilizations continue advancing technologically without destroying themselves, they'll eventually develop the capability to create sophisticated simulations, virtual realities indistinguishable from base reality. Motivation to simulate. Advanced civilizations might create many simulations for various reasons: research, entertainment, education, historical reconstruction, or curiosity about their own origins. Statistical argument. If advanced civilizations create many simulations, there could be vastly more simulated realities than base realities. Most conscious observers would find themselves in simulations rather than in base reality. Conclusion: if the above premises are true, it's statistically more likely that we're in a simulation than in base reality. This is a philosophical argument, not a scientific theory. It's not testable or falsifiable in the conventional sense, but it's an interesting lens through which to view the design question. If we're in a simulation, the designer is whoever programmed the simulation, an advanced civilization in a higher level of reality. From our perspective inside the simulation, this designer would be effectively godlike. They set the laws of physics, the simulation's rules, determined initial conditions, and could potentially intervene by altering the simulation's code. Evidence that might suggest we're in a simulation. Mathematical structure. The universe operates according to mathematical laws, which could be understood as code or algorithms running the simulation. Quantum mechanics. The observer-dependent nature of quantum mechanics, where particles exist in superposition until measured, resembles how simulations optimize computation by only rendering details when they're observed. Finite speed of light. The speed of light might be a speed limit imposed by the simulation's computational processing. Information can only propagate so fast through the system. Planck scale. The smallest meaningful length, Planck length, and time, Planck time, might represent the simulation's resolution limit, like pixels in a video game. Fine-tuning. The precisely set constants could be parameters the simulation's programmers chose to enable interesting outcomes like life. These are all speculative and can be explained by conventional physics without invoking simulation. But the simulation hypothesis provides an interesting framework. If Earth and the universe appear designed, perhaps they literally are, not by a supernatural deity, but by an advanced civilization creating a virtual reality. The simulation hypothesis doesn't solve the ultimate question of design, because it just pushes the question back a level. Who designed the civilization running our simulation? If that civilization is itself in a simulation, who's running that simulation? Unless there's an infinite regress of simulations, possible but mind-bending, eventually there must be a base reality. And we're back to asking whether that base reality is designed. But the simulation hypothesis does demonstrate that design doesn't necessarily require a supernatural explanation. A sufficiently advanced technology could create realities indistinguishable from ours, making the designer a natural rather than supernatural entity. The Fermi paradox. Where is everybody? Let's consider the Fermi paradox, named after physicist Enrico Fermi, who reportedly asked, "Where is everybody?" during a discussion about extraterrestrial life. The paradox is this: the universe is vast, hundreds of billions of galaxies, each containing hundreds of billions of stars, many or most with planets. If even a tiny fraction of planets develop life, and a tiny fraction of those develop intelligent life, and a tiny fraction of those become spacefaring civilizations, there should be many advanced civilizations in the galaxy. Some might be millions or billions of years older than us. Even traveling slower than light, a civilization could colonize the entire galaxy within a few million years. A blink in cosmic time. So where are they? Why don't we see evidence of alien civilizations? Radio signals, megastructures, von Neumann probes, terraformed planets. Why does the galaxy appear silent and empty? This is the Fermi paradox, and it has profound implications for the design question. Numerous explanations have been proposed. The Great Filter. Perhaps there's some barrier in the evolution of life and intelligence that almost no species passes. This filter could be behind us: life arising, evolving intelligence, developing technology, or ahead of us, avoiding self-destruction, becoming spacefaring. If the filter is ahead of us, we should be worried. It means most civilizations destroy themselves before spreading through space. Rare Earth. Perhaps Earth-like planets are extremely rare. The conditions required for complex life, the right star, right orbital position, large moon, plate tectonics, protective atmosphere, magnetic field, Jupiter-like guardian, stable climate, might be so specific that only a tiny fraction of planets have them. Life might be common, but complex intelligent life might be extraordinarily rare. The zoo hypothesis: advanced civilizations might exist, but deliberately avoid contact with primitive civilizations like ours, observing us from a distance like we observe animals in a zoo or wildlife preserve. They're here but unrecognizable. Perhaps advanced civilizations develop in ways we don't expect, using technologies or existing in forms we can't detect or recognize. Self-destruction. Perhaps intelligent species typically destroy themselves through war, environmental collapse, or other catastrophes shortly after developing technology capable of detection or space travel. From the design perspective, the Fermi paradox is interesting because it suggests Earth might be special. If the rare Earth explanation is correct, Earth is one of very few planets in the galaxy, possibly the only one, where complex intelligent life has arisen. This exceptionalism is consistent with design. If Earth was specifically designed for life, we wouldn't expect to find many similar planets arising by chance. Conversely, if life is common, and we just haven't detected it yet, that would argue against Earth being specially designed. In a universe full of life, our planet would be unremarkable, a natural outcome of universal processes rather than a unique creation. The resolution of the Fermi paradox has implications for the design hypothesis, though the implications aren't definitive in either direction. Consciousness, the ultimate mystery. Let's talk about consciousness, because it might be the most profound mystery related to design. What is consciousness? We all experience it, the subjective feeling of being aware, of having thoughts and sensations, of existing as a self. But explaining consciousness in physical terms is extraordinarily difficult. How does the activity of neurons in a brain produce the subjective experience of redness when you see a red apple? How does the firing of electrochemical signals create the feeling of pain, or love, or wonder? This is called the hard problem of consciousness, distinguished from the easy problems, which aren't easy, just more tractable, of explaining behavior, learning, perception, and other cognitive functions. The hard problem is explaining why there is subjective experience at all, why consciousness exists. Materialist philosophy holds that consciousness emerges from physical processes in the brain, that it's a product of neural activity, nothing more. When configured in the right way, performing the right computations, matter becomes conscious. There's nothing additional beyond the physical substrate. But this explanation feels incomplete to many people. How exactly does subjective experience emerge from objective physical processes? We can describe brain activity in complete physical detail. Neuron A fires, releases neurotransmitter B, activates neuron C, but nowhere in this description do we find the subjective sensation, the what it's like to experience something. Alternative views exist. Dualism. Perhaps mind and matter are different types of things. Physical processes occur in the brain, but consciousness is non-physical, somehow interacting with the brain, but not reducible to it. This is the classic Cartesian dualism, though it faces challenges explaining how non-physical consciousness interacts with physical matter. Panpsychism. Perhaps consciousness is a fundamental feature of reality, present to some degree in all matter. Complex brains have complex consciousness. Simple systems have simple consciousness. But consciousness itself is not something that emerges from organization. It's intrinsic to physical reality. This is an old idea, recently experiencing renewed philosophical interest. Idealism. Perhaps consciousness is the fundamental reality, and matter is an appearance or construction within consciousness. The physical world is what a universal consciousness looks like from within. This is a radical view that reverses the usual materialist assumption. Why? Does consciousness matter for the design question? Because consciousness seems to be the ultimate purpose of the universe from a human perspective. Matter and energy in itself has no inherent value or meaning. It just exists, following physical laws. But consciousness experiences existence, finds meaning, creates value. If the universe is designed, consciousness might be the goal. All the fine-tuning, all the precise conditions, all the complexity of evolution, perhaps it's all there to generate conscious observers who can experience, appreciate, and understand reality. From this perspective, the universe appears optimized for consciousness. The physical constants allow stars and planets. The chemistry allows life. Evolution produces complex organisms with sophisticated nervous systems. And somehow, mysteriously, consciousness emerges. The entire cosmic process seems directed toward creating awareness. This is, of course, highly speculative and anthropocentric. We value consciousness because we have it, but the universe's purpose might have nothing to do with consciousness. Or consciousness might be far more common than we think. Present in forms we don't recognize, in silicon-based life, in quantum coherent systems, in configurations we haven't imagined. But the existence of consciousness, its inexplicable nature, and its apparent centrality to meaning and value make it relevant to the design question. If you were designing a universe, creating conscious observers who could experience and appreciate that universe would be a reasonable goal. Our universe did produce conscious observers. Is this by design? The information question: is reality coded? Let's explore one more angle: information theory applied to physical reality. Information is a fundamental concept in physics. Quantum mechanics describes states as information. A particle's wave function contains information about where it might be found, what its momentum might be, and so on. The evolution of quantum systems is the evolution of information. Black holes, strangely, seem to have a maximum information storage capacity related to their surface area, not their volume. This leads to the holographic principle, the idea that all information in a three-dimensional region of space can be encoded on its two-dimensional boundary, like a hologram. This suggests something deep about the nature of space and information. The physicist John Wheeler proposed it from bit, the idea that physical reality, it, is ultimately based on information, bit. In this view, matter and energy are manifestations of information, and the universe is fundamentally computational or informational in nature. If reality is information, the design question becomes, who wrote the code? In computer science, information requires encoding, choices about how to represent data. If reality is information, there must be a language, a syntax, a structure in which that information is encoded. The laws of physics would be the rules of this encoding, and the physical constants would be parameters in the code. This perspective makes the universe look like software running on some kind of cosmic hardware. The hardware might be a mathematical structure, or quantum fields, or something even more fundamental we don't understand. The software is the specific laws and constants that govern how the universe evolves. If this view is correct, the universe was programmed. Programming requires a programmer, an intelligence that chose the laws, set the constants, designed the algorithms that run reality. This is another route to the design hypothesis. Not through biology, irreducible complexity, which has been largely debunked. Not through physics, fine-tuning, which can be addressed with anthropic principle or multiverse, but through information theory. If reality is fundamentally informational, information requires encoding. Encoding requires design. The counter-argument is that information in physics is just a useful description, not evidence that reality literally is information. Physical states happen to be describable using information theory, but that doesn't mean reality is actually software. The description is in our minds, not in nature itself, but the distinction is subtle and philosophical. If reality behaves exactly as if it were computational, if information is conserved and fundamental, if the universe evolves according to algorithms, then whether it's actually computation or just describable as computation might be a distinction without a difference. The purpose. Question: why anything? Let's step back to the biggest question of all. Why does anything exist? Why is there something rather than nothing? This is arguably the most profound question in philosophy. The universe exists. Space, time, matter, energy, laws, constants. But why? Why this universe? Why any universe? Why not simply nothing? The design hypothesis provides an answer. The universe exists because it was created by an intelligence that chose to create it. The designer had reasons, purposes, goals, desires that motivated creation. But this just pushes the question back. Why does the designer exist? If God created the universe, what created God? Theologians typically respond that God is necessary, eternal, uncreated, existing by the very nature of what God is. But this seems like a special pleading. Why can't we just say the universe itself is necessary and eternal, cutting out the middleman? The atheist position typically holds that the universe simply exists. It's a brute fact, requiring no further explanation. The universe doesn't have a purpose. It just is. Meaning and purpose are human concepts, applicable to human activities, but not to cosmic existence. The design position holds that purpose exists at a cosmic level, that the universe was created for reasons, that existence has meaning beyond what humans project onto it. This disagreement is fundamentally philosophical, not scientific. Science can investigate how the universe works, what its properties are, how it evolved, but science can't answer why it exists or whether it has a purpose. Those questions go beyond empirical investigation into the realm of metaphysics. From the perspective of someone wondering whether Earth was designed, the existence question matters because it frames how we interpret evidence. If you believe existence is purposeful, the fine-tuning and apparent optimization for life on Earth look like evidence of intentional design. If you believe existence is purposeless, the same evidence looks like selection bias. We happen to be on a habitable planet because we couldn't be elsewhere, and the universe's vastness guarantees some habitable planets exist. Both interpretations are consistent with the same observations. Your prior assumptions about purpose and design determine how you interpret the evidence. Living with uncertainty, as we approach the end of this journey, let's acknowledge something important. We don't have definitive answers. The question of whether Earth or the universe was designed remains open, contested, unresolved. The evidence for design includes Earth's optimal position in the habitable zone, the protective magnetic field, the stabilizing moon formed through an improbable collision, abundant water, despite Earth's formation, location, optimal atmospheric composition, plate tectonics, regulating climate, Jupiter's protective presence, fine-tuned physical constants, the mathematical nature of reality, ancient monuments incorporating sophisticated knowledge, the mystery of consciousness information as the basis of reality, the evidence against design, or at least the alternative explanations, include the anthropic principle. We necessarily observe conditions compatible with our existence. The multiverse hypothesis. Among countless universes, some permit life selection bias. We're on a habitable planet because we couldn't exist elsewhere. Natural processes. Each feature of Earth can be explained by physics and chemistry coincidence. With enough opportunities, unlikely outcomes become probable evolved perception. We see patterns and purpose because our brains evolved to detect them, even when none exist. Both perspectives are held by intelligent, informed people. Scientists, philosophers, theologians, and ordinary individuals look at the same universe and reach different conclusions. Perhaps the question, was Earth designed, is not the right question. Perhaps better questions are, what can we learn from examining Earth's properties? How can we better understand the conditions that enable life? What is the relationship between mathematics and physical reality? Why does the universe have the structure it does? What is the nature of existence and purpose? These questions are open-ended, inviting exploration rather than requiring definitive answers. They acknowledge mystery without demanding resolution. The universe might be designed. It might be random. It might be something else. Entirely. A mathematical structure that exists necessarily. A simulation running on higher-level hardware. One bubble in an infinite multiverse. Or something we haven't imagined yet. We don't know. And perhaps we can't know. At least not with certainty. At least not given our current understanding and capabilities. But the questioning itself is valuable. Asking whether Earth was designed makes us look more carefully at our planet's properties, appreciate the remarkable conditions that enable our existence, recognize the improbability of life, and contemplate our place in the cosmos. Whether or not there's a designer, Earth is extraordinary. The conditions that allow life are specific and rare. The universe has properties that enable stars, planets, chemistry, and consciousness. These facts are true regardless of whether they result from design or chance. Closing. The wonder of existence. As you drift towards sleep tonight, perhaps you'll think about the golden positioning of Earth in space, about the moon hanging in the sky, stabilizing our world, about the magnetic shield protecting us from solar wind, about the water covering our surface and filling our cells. Perhaps you'll contemplate the physical constants precisely set to allow atoms, stars, and galaxies. Perhaps you'll wonder about the mathematical laws governing reality, about the code underlying existence, about the information that might be the substrate of everything. Perhaps you'll look at your own consciousness, your own awareness, your own experience of being, and marvel at how matter organized itself, or was organized, into something capable of wondering about its own existence. Perhaps you'll feel small, recognizing that you're one human on one planet, orbiting one star among hundreds of billions, in one galaxy among hundreds of billions. Or perhaps you'll feel significant, recognizing that consciousness is rare and precious, that awareness is the universe knowing itself, that meaning exists because minds exist to create it. Whether Earth was designed or arose through natural processes, whether the universe has purpose or is purposeless, whether consciousness is fundamental or emergent, these questions remain open. The mystery persists, and perhaps that's how it should be. Mystery invites exploration. Questions drive science. Wonder motivates philosophy. Uncertainty keeps us humble. If Earth was designed, the designer left the question open, allowed room for doubt, created a universe that can be interpreted either way. The evidence isn't overwhelming in either direction. It's ambiguous, suggestive, open to interpretation. If that's intentional, perhaps the ambiguity itself is meaningful. Perhaps we're meant to wonder, to question, to seek understanding, while accepting we might never achieve certainty. If Earth wasn't designed, if we're the product of natural processes operating over billions of years, that's equally awe-inspiring. The fact that random physical and chemical processes operating according to mathematical laws can produce stars and planets and life and minds, that's extraordinary. That the universe contains the potential for consciousness within its initial conditions and physical laws, that matter can organize itself into beings capable of understanding matter. That's as close to miraculous as anything could be without requiring a miracle. Either way, designed or not, existence is remarkable. We're fortunate to experience it, to contemplate it, to wonder about it. So sleep well, knowing you're part of something vast and strange and beautiful. Whether that something was intended or accidental, whether it has cosmic purpose or only the purposes we create, whether reality was designed or emerged. You're here, aware, experiencing, thinking, wondering. That alone is extraordinary. The universe, designed or not, gave rise to you. Earth, crafted or accidental, provides your home. Life, planned or spontaneous, fills your body. Consciousness, fundamental or emergent, illuminates your mind. These gifts, these mysteries, these opportunities to exist and experience, they're here, now, real, regardless of their ultimate origins. Be grateful for them. Wonder about them. But don't let uncertainty about cosmic purpose prevent you from creating meaning in your own life, from connecting with others, from experiencing beauty and joy and love. The universe might be designed for you, or you might be a cosmic accident. Either way, you're here. Make it count. Experience fully. Love deeply. Wonder constantly. Good night, conscious being in a mysterious cosmos. May you dream of golden planets perfectly positioned, of physical constants precisely tuned, of mathematical elegance underlying reality, of the profound gift of awareness. And may you wake tomorrow to again experience this extraordinary world, whether it was designed for you or simply happens to host you. A world too beautiful, too complex, too perfect for words. A world inviting endless questions and offering no final answers. A world that is, miraculously and mysteriously, home. Sleep well, and thank you for wondering with me about the greatest question of all. Why are we here, on this perfect planet, in this vast cosmos, conscious and alive? The answer, whatever it is, includes you, part of the pattern, part of the design or the accident, part of the universe experiencing itself, part of the greatest mystery of all. Good night.